Hello and welcome to iitiansgateclasses once again. So today we are starting with dynamic programming. Okay, dynamic programming. So we are starting with a very simple example that is called Fibonacci series. And we see that what is a Fibonacci series? How can we code them? The recurrence function of the Fibonacci series and why there is a requirement of dynamic programming. Okay, so first of all, what is a Fibonacci series? So we know that at n equal to 0, we are starting from n equal to 0 till we go to some random number n, some given number n. Okay, n equal to, like, we will start from I equal to 0 and we will go till I equal to n. Okay, I equal to n. It is given that you have to generate Fibonacci series for I equal to n. Okay, so at 0, it's 0. At 1, it's 1. Then at second position, we will add these two and the result will be 1. Okay, and the third position, it will be, we'll add these two, the last two, and the sum will be 2. At the fourth position, we will add these two. Okay, and similarly, we will keep on generating the next number. Here it will be 3. If we add these two, it will be 5. If we add these two, it will be 8. If we add these two, it will be 13. And it will go like this. So this is a Fibonacci series. For example, this is 5th position, this is 6th position, this is 7th. Okay, so if somebody give you that what is the Fibonacci number for n equal to 100? Okay, so you can't simply go and keep on generating this. You will have to write a program that will automatically generate that number, right? Similarly, right now we are considering a small number n equal to 7, so our answer will be 13. If somebody asks to generate the Fibonacci series from 0 to 7, you will print this whole series, right? You will print this whole series. Let me repeat it again. At n equal to 0, the value is 0. At n equal to 1 or I equal to 1, the value is 1. Then you will just add the last two numbers. 0 plus 1. 1 will be there. 1 plus 1, 2. 2 plus 1, 3. 3 plus 2, 5. 5 plus 3, 8. 8 plus 50. 8 plus 5, 13. Okay, so this is a Fibonacci series. Let's see the recurrence function. What is the recurrence function? That using which we can represent a algorithm. Okay, so the algorithm for the Fibonacci series of Tn. So this is a function, okay, function of Fibonacci series. Okay, so we will say that, okay, let's do one thing. If n equal to 0 or n equal to 1, let's okay, so in general we can say that if n equal to 0 or n equal to 1, the answer is for n equal to 0, answer is, sorry, for n equal to 0, the answer is 0. For n equal to 1, answer is 1. Okay, so we'll write it like this. For n equal to 0, answer 0. Okay, if n equal to 1, answer is 1. Else means if n is greater than 1, we can write it like Tn minus 1 plus Tn minus 2. Okay, so what does it say? It says that just simply add last two numbers. For nth number, add n minus 1th number and n minus 2th number, or these function you can code. Okay, that's what it represents. So how can we represent this in a tree-like structure? Okay, let's write this Fibonacci function in tree-like structure. Okay, and there's one more way to write this down. For Tn, you'll say that the value is n if n equal to 0 or n equal to 1. Okay, in case of 0, it's 0. In case of 1, it's 1. If n is greater than 1, that case, just add last two numbers or last two function values. So whatever value this function returns and whatever value this function returns, the answer will be sum of these two functions. Okay, so using this recurrence relation, let's generate a tree. Like for example, for Fibonacci 7, we will calculate Fibonacci of 6 and Fibonacci of 5. We will add these two, but we don't know the Fibonacci of 6. Okay, so for that you will calculate Fibonacci of 5 and Fibonacci of 4. And for the 5, you will repeat the same thing. See right now what's happening. For 6, you are solving 5, as well as for 7, you are solving 5. So you are one more time solving this T5. Similarly, let's generate the whole tree in some other color also. So for T5, you will calculate T4 and T3 because you need to sum these up, right? I am calling the function calls. And here, what I will do, I will sum these two. I will sum this one and this one. Okay, if you see the recurrence relation here, I am summing up these two. So for T5, I need to sum T4 and T3. Okay, see here. If you replace n with 5, okay, so I need to sum n4 and n3, right? Sorry, T4 and T3, right? So that's what I am generating. I'm generating this tree recursively. Recursively means this function is calling itself. The function is T, it's calling itself. So for T5, I will calculate T4 and T3. And for T4, I will calculate this T3 and T2. For T4, again, I will calculate T3 and T2. Okay, for T3, I will calculate T2 and T1. And for 1, I know the answer. So I don't have any children for 1. We know that for n equal to 1, the answer is 1. See, for n equal to 1, answer is n, which is 1 here. For T1, T2, I have to calculate T1 and T0. Again, I have to calculate same thing. See, what's happening right now for a given sub problem. Right now, the given problem is T7 and the sub problem, which is smaller problem. Okay, the sub problem is, for example, for T7, the sub problem is T4. Now, how many times are you calling T4? Here you are calling T4. Here you are calling T4. And here you are calling T4. So once this tree is calculated, it's calculated. I already told you that this is calculated in this fashion. Okay, so I already messed this up. I have to create a tree again. T, for example, T3, T2, T2, T1, T1, T0, T1, T0. Okay, so I am drawing the line in which order these functions are called. Using red line, I am denoting that. And again, I will draw a line in that order, basically. These function will return the value. Okay, so here, first this function will be called. Okay, then T3 will be called, and T2 will be called, then T1 will be called. Okay, then T0 will be called, then T1 will be called, then T2, T1, T0. So this is the order. Okay, this flow. This is what? Root. This is root, then left, then right. Okay, so this is root, left child, right child. Okay, what is this order? I think this is root, left, right is in order or pre-order. So this is, I think, pre-order. In pre-order fashion, functions are being called. Okay, so we are calling, one second. Yeah, so this is pre-order. In pre-order, the functions are being called. Okay, so, and these functions will return the value in which order? First, it will return this value, T1. Then we will be getting this value. Then T2 will be calculated based on T1 and T0. Okay, so the return, this is the calling order. Calling order, okay. In which function are being called? This is calling order. And the returning of the solution. The returning of the solution are being done on first this child node will return, then this child node will return, then this will be calculated. Okay. Similarly, this will propagate to the root and we will get the answer at the root. So in which order the answer being returned? Left, right, and then root. Okay, so this is post order. So if somebody asks you in any exam or competition or any interview, you can say that in case of recursive function, we will follow for calling order, it's pre-order. Root will be called first, then left will be called, then right will be called. Okay. And in case of returning, the post order will be followed. Left will be called first, right will be called first, and then root will return. Oh, sorry, left will be returned, then right will return, then root will return. Okay, so this is the returning order. Now, once I return the value of T1, okay, I return the value of T1, or you can say I called T1 already. If I call T1 or sold, I have already sold the T1 here. Okay, using green. I have already sold the T1 here. Then why am I solving T1? Because the value will be same, right? It's 1. If I already sold the T2 here, the calling will be followed in this fashion. This T2 will be called after this T2, right? So once I sold this T2 here, why am I solving this again? This makes no sense. For dynamic programming, it says that if you have already solved the problem, why are you solving it again? Let's try to save it in some memory. Okay, so you don't have to solve here. You don't have to solve here. Okay, so let's see this again, this tree. If we induce a memory into it, okay, if we induce some memory into it, let's see this tree structure again. Okay, we will say that, okay, T4 will be called, T3 will be called. Okay, this part of tree I will calculate later on because the calling order is in pre-order fashion, like right, root, then left, then T2 will be called, then T1 will be called. Okay, in this fashion I am calling this. So for that, let's create an array, and we will say that, okay, we will say that, okay, this will be 0, 1. Okay, so let's create a memory for the solutions, for the sub-problem solution, for the intermediate problem solution. You know that the root problem is T4. And for that, we have to solve T3, T2, and T1, right? So let's try to save this. That, okay, for T0, we will save the solution at 0th position. For 1, we will save at first position of an array. So we are considering an array to save the solutions. Okay, at second, 3 and 4. Okay, so we have these many positions. So right now, whenever we are calling a function, we will create the position for that. We are assuming that we'll create the problem, right? But for a given problem, we already know what is the sub problems, how many sub problems we have. So we create a space for that. We already created the space for that. Okay, so in this fashion, these are being called. Once T1 is returned, we know that the answer of T1 is 1. Okay, it will be saved here in the array. It will be saved here in the array. Let me use some other color. Okay, then T2 will call T0. Okay, then T2 will return. So we are returning in post order fashion. Okay, first left child will return, then right child will return. So we saved the T1 solution here in the space, given memory, you can say. T0 will be saved here. It's not already solved. If it's already solved, if there is something in the array, if array is blank, then we call the function. If there is something in the array, we don't call the function at all. Okay, so now T3 will call T2 as well as T1 here. But T1 is already solved. You can see T1 is already solved. So it won't call T2. It will say that, okay, let's not solve T1 because it's already solved. It's saved here at this location. And we know the answer, it's 1. Don't call a recursive function again. It's already solved, right? That's what dynamic programming is. To use some extra memory or induce some space for already solved a sub-problem so that you don't have to solve that sub-problem again in some other branch of the tree or recursive function. Okay, it says that it's 1, right? Now, okay, before calling to T1, T2 is solved. T2 is solved, and the value of T2 is, sorry, for 0 is 1, 0. For 1 is 1, and for 2 is it's 1. Okay, 2 is 1. You can see the Fibonacci series. Okay, it's 0, 1, 1, 2, 3, right? So 0, 1, 1. Now T3 will try to call T2, but before calling, sorry, T3 will try to call T1, but before calling T1, it will see that if there is a solution for T1. already sold. Yeah, it's already sold. So don't call T1 at all. Don't call T1 at all. If it's already sold, why do we need to call the recursive function? Okay, so we know that its value is 1. Now T3 will be calculated and its value will be 2. Now for T3, the value is 2, right? We already know. And to solve the T4, we need T3 as well as T2. So T4, before calling T2, it will check whether there is an answer for T2. Okay, it's there. It's there, right? For this array, we made it clear that whichever position we are looking, that is the answer for that recursive solution. Okay, it may be different for other problems. We might be using some matrix, hash map, or any other data structure, right? For now, I am taking the easiest data structure array to store the solution. Okay, so it will say that, okay, we don't have to call T2, it's already solved and it's stored in array. So don't call T2, its answer is 1. Let's sum it up. If we sum these two, 2 and 1, answer is 3. And we know that for T4, answer is 3. Okay, T4, the answer is 3. So see, we prune this whole tree. We prune this whole tree, pruned it. For we didn't generate, because whatever we were supposed to generate here, we already sold it here. Okay, we already sold it and we saved it in array. And we have seen that, okay, if it's in array, it's already sold. We don't have to create this whole tree. Now let's see how much time did we save. What is the time complexity reduction? What is the benefit that we gained using this algorithm? Let's see. Okay, let's create a non-pruned tree for T5, for example, or without dynamic programming. Okay, I'm just generating the tree. T0, T1, T0, T2, T1, T0, sorry, T1, T0. So this is the whole tree. What is the maximum depth of the tree? It's n. See, 5, 4, 3, 2, 1. If n equal to 5, what is the depth? It's n. N is the maximum depth. In case of depth, the maximum number of nodes, you can count it. For example, if my depth is 2, what is the number of nodes? 1, 2, 3, 4, 5, 6, 7. It's if my depth is 1 and 2. Okay, the number of node in the tree, you can consider number of level. Okay, if my number of level is 1, 2, and 3. If number of level are 3, number of nodes are 2 raised to power 3 minus 1. So if number of level are 1, 2, 3, 4, 5. Okay, the number of maximum nodes a tree can have is 2 raised to power 5 minus 1. Okay, and to solve each solution, we are taking just one single sum, which is order of 1. Okay, for each node is taking order of 1. Each node is taking order of 1. How many nodes do we have in total? If for n, it's 2 raised to power n minus 1. Okay, see here. If we have n levels, we have 2 raised to power n minus 1 nodes. So what is the effort to solve this Fibonacci tree? It's almost 2 raised to power n minus 1. How many levels do we have maximum? 1, 2, 3, 4. It's not complete, but in worst case, when n is too large, it's 2 raised to power n minus 1. So it's order of 2n. Order of 2n, which is very, very high. Very, very high. Okay. So once we use dynamic programming, what is our time complexity? Okay, so for the same example, T5, let's use dynamic programming. We have saved the solution. So we are going to call the function in pre-order fashion and return it and try to save it. So I am going to have some extra space of 0, 1, 2, 3, 4, and 5. Okay. So T4, then T3, then T2, then T1. Okay. So for T1, the solution will be saved here. For example, it's 1. We know that it's 1. And for T0, it's not solved. There is no solution in T0. So we have to call T0 also. So it will be saved here. It's 0. For T3, I won't be calling anything. Because T3, I am going to call T2 as well as T1. T1 is supposed to be there, but I'm not going to call it because it's already solved, right? So I will save T3, T2 here, which is 1, T3 here, which is 2. Then for T4, I have to call T3 as well as T2. I'm not going to call T2 because it's already solved. Okay. So I will save the result in T4. T4 will be 3. Okay. And for this T4 as well, T3 will be called, but T3 is already solved and saved at third location. We know that it's already solved. So we are not going to call anything. So it will be how much? 5 here. Now, how many nodes do we have in the tree? How many nodes do we have? It's n plus 1 nodes only. See, 1, 2, 3, 4, 5, and 6. N plus 1 nodes. You can create the same tree for T100. You will have 101 nodes. So our effort is order of n plus 1, which is equal to order of n actually. So see, we reduce the effort from 2 raised to power n using dynamic programming. We reduce the effort from 2 raised to power n to order of n. See how big that effort is. Okay, so this much time complexity we reduce. So for Fibonacci series, okay, let me try to write this in good writing, a better writing, not good, but better. For Fibonacci series, without dynamic programming, it will be order of 2 raised to power n. With dynamic programming, it will be to order of n. Okay, that is huge actually. That is huge. So let's see one more example, which is 0-1 knapsack. 0-1 knapsack. Okay. So what is 0-1 knapsack? First, let me define the problem. If you remember the partial knapsack or fractional knapsack, previously we solved something called knapsack. The real name of that knapsack is actually fractional knapsack, KS. I will represent knapsack as KS. Okay. So in that one, what is the problem? The problem that you are given with a bag, or you can call it knapsack, with a fixed capacity, that you can fill that bag with at max this much weight. Okay, and you are given n items like item 1, item 2, item 3, item 4, item 5, something like that. Item n, you are given with n items with its weights. Okay, W1, W2, any weight, W3, Wn. Okay, and its profit also, P1, P2, P3, some Pn. Okay, and you have to include the items such a manner that you maximize the profit. So you don't include a item whose weight is very high and its profit is less. So what was the algorithm? It was greedy approach. Type of algorithm was greedy. And there we calculated profit per kg or profit per unit weight where basically you divided P1 with W1, P1 with W1, P2 with W2, P3 with W3, okay, and Pn with Wn. You sort these profits, okay, and you considered a profit per unit weight, whichever is maximum. You sort this out and you consider the maximum one, and you include that into the knapsack. Why did we do that? Because we can include the item in partial manner or in fractional. We can split the item. We don't have to include the whole weight, W1. We can consider a weight W something which is less than W1. But here in 01 knapsack, it's not allowed. You can't split the item. You can't break the item. Either you will consider the whole W1 or you cannot consider it. So let me write a choice diagram. Why are we writing choice diagram for 01 knapsack? It's for 01 knapsack, 01 KS, okay, 01 knapsack. Because for each item, we have a choice. Either to include this whole item as it is, or don't include it, okay? So we don't know. Till the whole algorithm is complete, we don't know which item to include and which item we should not. We don't know that, okay? If we know, the problem is already solved, okay? So we don't know which one to include and which one to reject. So what do we do? What do we do in that case? We will create a choice diagram, and based on this choice diagram, we will have a algorithm, 01 knapsack algorithm. And it's without the memory. So what I'm saying is, it's a recursive solution. Recursive solution like this. In Fibonacci series, we had a recursive solution. So this is a recurrence function. Recurrence function is corresponding to recursive solution, right? Recursive solution. But we don't have a memory here. So in 01 knapsack also, we will try to induce the memory and reduce the time complexity, or we will eliminate the possibility of calculating same sub-problem again. That's what dynamic programming says. It says that if there is a recursive solution, eliminate a possibility of having same sub-problem, eliminate a possibility of solving same sub-problem. So your time complexity reduces. So in 01 knapsack, what is the choice diagram? Okay, so we are iterating item I from first item to nth item. Okay, we are iterating it from first to nth item, right? And we are saying that if Wi is greater than current capacity, current item which we have picked, its weight is greater than current capacity. So just do one thing, do I equal to I plus 1, okay? And again go back here. Again go back here and repeat the same step. If this is true, if this is false, we have two choices here. Either to include this item or don't include this item, because this item may be part of optimal solution, which gives us maximum profit, or it don't give us maximum profit. That's what we are saying, okay? So if we consider that this item is a part of optimal solution, let's do one thing. Let's do include it, okay? Let's make it the part of the profit. So optimal profit will be basically P. Let's consider the optimal profit is capital P. It will be P equal to P plus PI. Okay. Current item profit will be included in our optimal profit, and our capacity will be reduced because we added the current item into the bag. Okay, we added the item into this. So this is our bag. And we are iterating the item W1, W2, W3, W4 with profit P1, P2, P3, P4. So here, for example, if I equal to 2, we decided that let's add this into our bag. So this profit will be the part of optimal profit. If we are assuming that P is the optimal profit, okay, optimal profit, here it's PI, okay. And this capacity will reduce, okay, because we are filling this bag with this item W2. Okay, so W equal to capacity minus WI. And we do I equal to I plus 1. And we go back to this step. Now go back step, I will repeat with this. We go back to this step and iterate the same thing again. Here we say that, okay, let's not include this. It may be not the part of this current item, maybe not the part of optimal solution. Let's not do anything. Just do I equal to I plus 1 and go back to the first step. So this is the algorithm. This is the algorithm of choice diagram of the algorithm. We are iterating over all the items. We didn't sort any of the item, okay? And what we are saying that if the weight of current item is greater than our capacity, we just simply go to the next item, okay? Else we have two choices: include the item or don't include the item. If we don't include the item, just go to the next item. Don't do anything. If we have included the item, we will add the profit of current item to our optimal profit, that we will consider that this will be the optimal profit, okay? And we reduce the capacity because we have added that item into our bag or knapsack, and we will go back to the next item and iterate this. So this is our choice diagram. So choice diagram will make you understand the algorithm. This is the algorithm. So let's try to write this algorithm in like a recursive manner. So I'm saying that 0, 1 knapsack. This is our capacity. This is our capacity. Okay. This is our current capacity. This is our current item. So instead of going from 0 to n, we are going from n to 0. Okay. And we are saying that if W capacity is less than equal to 0, or you can say 0, capacity is less than equal to 0, or the capacity cannot go in negative. So we will say that if capacity equal current capacity, we are iterating over items, right? If current capacity is 0 or n equal 0. So we have already iterated all the items because we are going from n to 0. We have considered last item first. It doesn't really matter which item do you consider first. Okay. So you say that, okay, return 0. We have processed all the items. Okay, so you return 0. Else, what you will do, this is like exceeded the capacity, or you can say that processed all the items. Processed all the items. This is what this is saying. Else we will say that let's compare the weight. If weight array, this is the weight array WTN. If WTN is basically greater than W, we are going from n to 0, right? We have picked the last item first. We have picked the last item for the processing first, and then second last, then third last, and we will iterate it till 0. Okay. So we are saying that if weight of the current item, which is in n, the current item is in n, greater than the capacity, then we can't do anything. Just call the same function again. Return 0, 1 knapsack W, n minus 1. Okay. Else you have two choices. Okay. So whichever is maximum, you will return that. You will say that, okay, return maximum of, for example, P is the, WT is the weight array, P is the profit array. Okay. So you will say that return maximum of these two, P profit array, P of N. So it will confuse, the P will confuse you. I will write profit as PR, not P, okay, PR. PR is the profit array. PR of N plus 01 knapsack, 01 knapsack. I have considered the current item, so I will have to reduce it from our capacity now. And we will say that, okay, and this is the profit that will return. Either this is this one and N minus 1. Let's move on to the next item. Either this will be your maximum profit, or let's not consider the current item. 01 knapsack, W comma N minus 1. That's it. So this is 01 knapsack. So if you go back to the choice diagram, try to understand the choice diagram and try to understand this recursive function, you will understand it better that, okay, what is it that we are doing? This is the base condition where we are saying that, okay, either we have processed all the item or the capacity is 0. We can't do anything. Let's move on. Let's return 0. Or the current item weight is greater than the remaining capacity of the bag. Just move on to the next item, okay, which is at one less index. If this is not the case, we can consider the current item by adding the profit to other remaining recursive calls, or we can drop the current item by simply moving on to the next item. Okay, so this is 01 knapsack. Now let's do the time complexity analysis for 01 knapsack by building an example in a tree manner, so you understand it well that what is going on here. So if any interviews, somebody asks you 01 knapsack, you can answer it. There are so many variations of 01 knapsack, like target sum, subset sum, and there are so many variations of 01 knapsack. I will give you, after completing 2-3 more examples, 2-3 more algorithms of a dynamic programming. I will give you a list of algorithms or list of variation of 01 knapsack, which are quite easy to find out once you know 01 knapsack. Okay, so this is our example. Let's note it down. What does it say? It says that, okay, capacity is 16. It is given the capacity is 16. Our profits PR array goes like 25, 75, okay, 15, 20, and 35. So we have 5 items only, like 1, 2, 3, 4, and 5 items. This is the weight array for each item. It's 10, 7, 2, 5, 2. Okay. So now let's build a tree. So initially, we will start with, let me pick some other color, 01 knapsack. We'll start with 16. 16 is our capacity, and we will start with the 5th item. Okay, see the algorithm. So we call 01 knapsack as 01 knapsack 16, 5. Initially, we are going from 5 to 0. Okay, like 5, 4, 3, 2, 1, like this. So we are iterating the index from maximum 1 to the lowest one, okay, minimum 1. So we'll call 01 knapsack like 16 and 5. Then how our current profit here is current optimal profit here is 0. So in this branch, we will compare the weight of 5th item. It's 2, which is basically, look at the algorithm, right? We will compare the weight. It's less than the capacity. 2 is less than 16, right? So we have 2 choices, either to include this item or we can neglect this item. Okay, so we have 2 choices. So here on the left side, I'm saying that I have included the item. So the capacity will reduce from 16 minus 2 to 14. Okay, So it's 14,4. Here I haven't included the item. Here I have included the item. Here I haven't included the fifth item. So my capacity will remain same. It will be 16, and I move on to the next item. So what does this branch says that? Let's assume that the current item is the part of optimal solution, and this branch says that let's assume that current item is not the part of optimal solution. Okay. So similarly, we will construct the tree. For time analysis, I'm not calculating the optimal profit, but I'm calling number of calls we are making. That will give us time complexity. Okay, and then we call 0, 1 knapsack. And here we consider the fourth item. So capacity will be 9 as well as 3. Here we won't consider it 14,3. Here we consider this item. Capacity will be 7,2. Okay. Here it's here we won't consider it, so it will be 9,2. Then we include this item. It's 0,1. Okay. After the capacity is 0, we can't call further. We can't call this 0, 1 knapsack further. Okay. And if we haven't included, it's G7,1. In 7,1, let's see if we can call this one. We cannot call. Okay. We cannot call. So if we select the first item, the weight of the first item is greater than 7, the current capacity. So we can't use it. Okay, we can't use it. And here we haven't chosen this item, first item. And then 9 and 2 also have branches. Like on the left side, we include the second item. So our capacity will be 2,1. Remaining capacity will be 2. 9 minus 7 is 2. Okay. And here we the second item will not be the part. So 9,1. Okay. So the current capacity is 2 here, and our item is the first item, which have the wait time which is greater than 2. So we can't call, and this tree will remain till here. In 9,1, let's include this. We cannot include. Okay, because 9 is less than 10, so we can't include it. And here we say that, okay, let's not include the item. Right. So similarly, we grow the other tree structure also. So here we say that, okay, let's include the third item. If we include third item, our capacity, third item weight is 2. So our capacity will reduce to 12. If we haven't included a third item, our capacity will remain same. Okay, let's include the second item. Our capacity will be like how much? 5. 12 minus 7 is 5. Let's not include it. 12,1. Okay. Similarly, the tree will grow. Once you build this whole tree, there are so many calls happening. You will notice that there are how many calls at max? At max. This is W. And this is N. How many calls are there in total? There are possibly n levels again. So we will have 2 raised to power n nodes for calls, function calls. So our time complexity will be 2 raised to power n. Okay. Instead of doing this, what we will say that, okay, let's have a memory for dynamic programming where we will save this mapping that for 14,4, what is the solution? For example, here we will say that for 0, wherever W current capacity is 0 and N is equal to 1, what is our solution? Let's save it. Let's save this solution. Similarly, for this one, save the solution for 7,2. W equal to 7, N equal to 2. Let's save this solution. In the first subproblem. Subproblem is where capacity is 7 and we are at second item and we are going from 1 and the first item only. Okay. So W 7, 0, 1 knapsack 7, 2 will be saved in a memory like some hash map. I will explain what hash map is in data structure course, but first assume that we already saved a answer for 7,2. Then at some tree here we have 7,2. On the right side, if again we have some 7,2, we won't solve it again. So there are how many possibilities of nodes? How many possible solution can we save? If we have the capacity W and N, there can be possibly distinct how many calls? W multiplied by N calls can be there. So now we saved it in a memory. So we'll never save. For example, if we have 16,5, we can save 9,2 somewhere. We can save let's consider a very small number. Okay, W is 4, N is 3. So how many distinct call of knapsack can be there? How many distinct calls? Okay, it can be 4, 3, like 4, 2, 4, 1. Okay, similarly we can have 3, 3, 3, 2, 3, 1. Similarly, we can have 2, 3, 2, 2, 2, 1, 1, 3, 1, 2, 1, 1. Okay. So how many possibility can we have? 12. Okay. If you sum it up, it's 12. 12 distinct possibility of 0,1 knapsack we can have. So if we store all these possible answers, we will never have to solve 4, 2 elsewhere in the tree, elsewhere in the recursive call. Okay. So what is the time complexity now? It's order of W. W is the capacity, the maximum capacity of knapsack multiplied by N. So we reduced without dynamic programming. It's 0,1 knapsack without dynamic programming. Dynamic programming, it's how much? Order of 2 raised to power N, where N are equal to number of items. With dynamic programming, how much? It's order of capacity multiplied by N. W is the capacity, okay? W multiplied by N. So it's Wn basically. So we reduce this, and there is a huge difference between them. If value of N is too high, okay, then in that case, this will win. That is the power of dynamic programming. So that's it for today, students. Thank you all for joining.